Everyone. I'm going to be talking about my lab one for physics, which is about an object with a constant velocity. So to do this, I kicked a soccer ball in the Kulk, and I started the video after the ball had been kicked. So the only force that's acting on the ball will be normal force and gravity, which will cancel each other out, and then friction, which should be very small. Um, and then I tracked its position throughout the video using the tracker app, like manually placing the positions on the ball during using the time increments it gives me. So let me play the video of the ball. And so you can see here that the position versus time graph for the ball is the slope is relatively flat, like it doesn't change too much. So the line is pretty good. It's not perfect, obviously, but then I had to make a computational model, and I had to find an initial velocity for that computational model. So what I did was I took the first two time increments, calculated the difference in time, which is just 0.033, and then the distance in position, so 0.112 minus approximately 0.005. And then I found an initial velocity using those two numbers, which let me pull up the computational model, which I found to be 3.24 in the x direction, 3.24 meters per second. And then the initial position was around 0.005, as I previously stated. The mass is not important for this. Mass wasn't used in any of the calculations. So then delta t, the size of each time step, is important here because every time it loops, it goes through that time increment, and the position changes by 0.0324, which I just found using the initial velocity vector. And then if the velocity is constant and the time increment 0.01, then it's just going to be velocity times time, which is just 0.0324. Um, and then what I found after that was I just ran the code, and let me show you what I came up with. So the predicted final position is around 8.28. Obviously a straight line in this model, just using the initial velocity that I found using tracker. So let's compare that to the actual. 5.385. So as you can see, it was not a very good prediction. It could have been a lot better. But let me explain why this was. First off, the jump in position for the first time increment was much greater than essentially every other position jump in every other time increment. So you see the jump right here is over 0.1. But you look at this one, it's not over 0.1. This one, not over 0.1. You keep going down, not over 0.1. So the initial position jump was much greater than every other one, which I attribute mainly to human error. I probably clicked it a little wrong when I was doing the lab. I tried to be as accurate as possible, but clearly I wasn't. And also, one other thing, the computational model didn't account whatsoever for the frictional force because I had no way of calculating it. So the number the number in real life is going to end up the final position is going to be less than the final position in the model because the final position in real life, the frictional force is obviously acting on the ball, but the model has no way of knowing that. The model just predicts the final position given the initial velocity and the amount of time I gave it. The amount of time was 2.537 seconds, and the velocity is 3.240. So yeah, essentially that's how I got all that. It was off by a good bit, but that's down to mainly human error. Also, one more thing I'd like to discuss is what would happen if I determined that going to the right was the negative direction instead of the positive direction. So the position time graph would look very similar. The magnitude of the slope, or the absolute value of the slope, would be the same. However, the curve would go. Sorry, let me. The curve would go down where my mouse is headed, rather than going up there. So it would be pointed in the negative x direction, obviously starting from the origin, rather than going up, because it would just be turned negative. So yeah.